Hello and welcome to Empowered Learning. This video will be about complex numbers. Specifically, our objectives will be to define what a complex number is, to be able to learn how to add, subtract, and multiply complex numbers. Also, to learn what the powers of I actually mean, and using that to be able to eventually divide complex numbers, and why we have to go through a whole special process of dividing complex numbers as well. From there, we'll also explore the principal roots of negative numbers and the discriminant and complex solutions to equations. And that's just a fancy way of saying whenever we use the quadratic formula, whenever we have answers where the discriminant or the expression that is under the square root sign is negative, then we end up having what we call complex conjugate solutions. So we'll talk about that as well. So moving forward here, I have a lot of verbiage right here, but basically what I'm trying to say is that whenever we have quadratic equations where our answers end up being numbers that have negative numbers under a square root sign, we know that technically those numbers aren't real. And so whenever we have these types of solutions, we call them complex numbers, and the complex number system was actually birthed out of being able to say, all right, if I change one thing about a basic algebraic system and allow negative numbers under an even nth root, what will my numbers look like? What will my numbers act like? And will they follow the same rules as an algebra? Because algebra is really a mathematical structure, not a math subject, so to speak. And with this mathematical structure, it has rules and elements and rules and things that it has to follow, 32 rules to be exact. And so, of course, one of those rules is not being able to have negative numbers under even nth root signs, like square root signs or fourth root signs. But if we change that rule and then run through the rest of them, we see how our numbers act. Now, complex numbers are used in applications such as electrical circuits in trying to characterize, let's say, and I'll put in air quotes, the resistance of a capacitor or an inductor, because capacitors and inductors don't necessarily act like resistors. But of course, if you're not in that field, you may not understand that, but that's fine. But the main thing I want to get across is that there are applications for using complex numbers. And so our job here is not to talk about that, but to try to get a good understanding of how to be able to work with complex numbers, so that when you're in courses or in situations where you actually have to use complex numbers, you can navigate them okay. All right, so we know that the complex number system is the same as the real number system, except for one rule: square root of a negative number is not allowed. And to be specific on this, it's more than just the square root of a negative number. I really should be saying the even nth root of a negative number is allowed, okay? But we use the square root as sort of a base to be able to sort of define this. So the basis of the complex numbers is an imaginary number I, and we define it as just square root of -1, okay? And we know that the complex numbers, they're actually an extension of the real number system. And of course, it's an extension because we'll find out here in just a second that these numbers are formed by the sum of a real number as well as an imaginary number. And the way that these numbers look, their standard form, you have A, which is the real number, and you have B times I, which is the imaginary part of the number. So this is why I say that the complex numbers is an extension of the real number system, because as long as you have any real number here, any real number that you want, you can put in for A. But as you see, we're adding to, or in some cases, we'll be subtracting a whole nother set of types of numbers, which are which are imaginary. And having imaginary and real, add that together, we end up with the complex number system. So to talk about some basic facts about our complex number here, we know if A is equal to 0 here, then of course this goes away and our number is just purely imaginary. Okay. Now, of course, if B is equal to 0, then that means it makes the second term go away and our number here is purely a real number at that point. Okay. And of course, if we have two complex numbers that are equal to each other here, then we know that the real part has to equal the real part and the imaginary part has to equal the imaginary part. So that's what we're saying here. And in particular, the coefficient that goes along with the imaginary part, those things are equal. And for this last basic fact, we're basically doing the definition of subtraction as it looks with complex numbers. We know from just regular real numbers that A minus B is the same as A plus the negative of B. And so all we're doing is just extending that fact to the complex numbers. So now what we want to do is figure out how do we add and subtract complex numbers. So it turns out that adding and subtracting complex numbers is relatively simple. Just like how in regular algebra, whenever we combine like terms for an expression, we kind of do the same thing here. If we look at the real number part of each complex number as apples and the imaginary part as oranges, we just put apples with apples, oranges with oranges. So you see here, if we're adding complex number, we add reals with reals and imaginaries with imaginaries. Okay. Whenever we are subtracting, notice that we have to distribute the understood -1 first, and we'll end up with A plus BI minus C minus DI. Hold on. Minus DI. And then here, the A and minus C goes together, and the B and the minus DI go together here. And that's pretty much it when it comes to adding and subtracting complex numbers. Whenever we multiply complex numbers, we multiply them the same exact way as if we were to multiply a regular binomial. Okay. So for instance, if I had something like x plus 1 times x minus 3, we know that we could use the FOIL method to multiply that, or there's other ways to do it, box method, however you like to multiply two binomials. We could do the same exact thing using complex numbers. So the one thing that's different though is that with complex numbers, whenever we start to multiply two imaginary parts or imaginary numbers together, that's where things start to change a bit. Okay. And in particular, whenever we have, let's say, a complex number and it is being multiplied times its conjugate here, and I'm going to scroll up so that you can see this. And a conjugate is just a conjugate expression is just an expression where everything is the same for that binomial type of expression except for the sign. So you see for this one, this is plus and that's minus. So if we were to actually do the FOIL method on all of this and multiply it out, you'll see that this is the outcome that we would get. And we see how these two middle terms here cancel to 0. And we also see that if by definition I is equal to square root of -1, then I squared, which is just I times I, would be a -1. So here, this portion, the I squared, becomes a -1. And of course, those two terms in the middle cancel, and we end up getting A squared plus B squared. Now, what's happening here is one of the things that normally happens in, I guess, mathematical systems that are based upon a lower math system. So for instance, the complex number system is really based, or its foundation is in the real number system. And so there is always an operation that happens. Let's say if you're building the complex number system from the real number system, there's always an operation that you can do in the higher system that will bring you down to the lower one. And of course, anytime you multiply a complex number times its conjugate, you end up getting a real number as a result. Because if you look here, we know A is a real number, B is a real number. Okay. We know that this part BI is only imaginary when we actually have the I in it. But since I squared is -1, we have a real number here times another real number here. And so any real plus another real gives you a real number. So hence, anytime we multiply a complex number times its conjugate, we end up getting a real number as a result. And it turns out that's actually how we're going to figure out how to properly divide complex numbers as well. And we'll talk about that a little bit later. So we see here for complex number a plus bi and its conjugate. And if you're just represented by a letter, we normally just put a line over it for that. Then these are called conjugates. And for the complex number, it's always true that the product of a complex number and its conjugate gives you a real number result. So that's what I was trying to get at. So in general, whenever we are multiplying two complex numbers, and let's say they're not conjugates of each other, this is an example of what it looks like whenever we multiply it out. And so using the FOIL method, we'll do first, outside, inside, and last. So that's what these four terms are. And then of course you see both terms that have the i's in them will be combined together. This term is not considered a like term with these other two because we know I squared could just equal -1. And thus this term here is really just a minus BD. So that's why it gets paired up with AC here. All right, so if we're going to do some practical examples here for this first one, again, we just put real with real and imaginary with imaginary. So real number, and we'll add that to imaginary plus imaginary. And our result, -3 plus 5 is a +2. And 2i minus 6i is a -4i. For the second example, notice that we have to distribute the understood -1 first. And so when I write this, I'm just going to drop the parenthesis on all of these, kind of make this a bit more simple to follow. So from here, we have apples and apples, oranges and oranges. So we got 6 minus 3, that one, and then plus -7 plus -7i plus 4i. And so our result here ends up being 3 minus 3i, because 6 minus 3 is 3, and then -7i plus 4i is a -3i. So if we were to work out this next one, again, we would have to distribute the understood negative to both terms. So this is 14 plus I plus 13 plus 2i. And then again, we combine like terms, apples with apples, oranges with oranges. And we see 14 plus 13 goes together, plus I plus 2i. So 14 plus 13 is 27. And 1i plus 2i is 3i. And then finally, for this last example here, notice that this is 0. So this is like this term is not even here. And all we have is this real part here. So we have real with real. So that's 8 minus 7 plus only term that's imaginary is going to be the 2i, because of course 0i plus 2i is just going to be 2i. And the result ends up just being 1 plus 2i. So moving on, so now we've already done the adding and subtracting. We're going to go ahead and practice multiplying now. So here we know that we have this minus 3i being multiplied times a complex number here. So we're just going to distribute. And a negative 3i times 5 would be a minus 15i. And a negative 3i times a positive 2i would be a minus 6i squared. And if you remember, I squared is just square root of negative 1 times itself. So by definition, that ends up being a negative 1. And of course, oops, forgot to put the I here. That should be 15i. And so here a negative times a negative ends up being a positive. So our final number should be 6 plus 15i. And notice that I turned this around because we always want our complex numbers to read real number first and then imaginary number last. Okay. For example F, we're just going to do FOIL method. So 4 times 6 is 24. Outer, 4 times 2i is 8i. Inner, negative 1i times 6, so minus 6i. And then last, we have negative I times 2i. That would be a minus 2i squared. And of course, from here we realize that 8i and 6i combine to be 2i. And that I squared here is a negative 1. So the negative times a negative actually ends up being a positive. And of course 24 plus 2 is 26. So our final answer ends up here being 26 plus 2i. So for this next example, please note that this complex number and this one are both conjugates of each other. And so remember, we learned that whenever we have a complex number being multiplied times its conjugate, the shortcut is just to know that the answer is just going to be a squared plus b squared, and that's going to equal out being a real number. I'm going to work it both ways so that you see that that indeed is true. I'm going to go ahead and do it the long way first on purpose and then do it the short way. So here, negative 4 times negative 4 is a positive 16. And then the outer part, negative 4 times a negative 8i is a positive 32i. Do the inner, 8i times 4 is a 8i times a negative 4 is a negative 32i. And then 8i times a negative 8i is a negative 64i squared. These two middle terms cancel to 0. And we see that I squared ends up being negative 1. And of course, a negative times a negative ends up being a positive here. And so we just end up having 16 plus 64 here. and that ends up being 80 at the end of the day. Now, if we were to take the shortcut, we would see here that in doing it this way, we would just have A would be a -4, so we just take that and square it, plus B, we're going to say that that is 8, and we square that. And we see we still end up with 80. So whenever you recognize you have a complex number and you're multiplying it times its conjugate, you don't have to do all this business here. You can just remember that you identify A and B, it's just going to be A squared plus B squared. Now, for example, H, we realize that the real number part is 0, so we could actually rewrite this way. And here, it's pretty simple. Just multiply 4i times -13i. -13 times 4 is going to give us a -52. And I times I will be I squared. And again, I squared is understood to be -1. So in this case, we see that our answer actually ends up being a positive 52. So the next concept that we want to talk about is what happens whenever we have powers of I. Meaning, if you remember how in the last example that I had, we were taking, let's say, -4i and multiplying it times 13i. Believe that was it. And notice here we have the I times I, which was I squared. Well, what if I had the same situation here? And let me erase this. What if I was multiplying by 3 of these imaginary numbers? So let's say I had 2i times 4i times I. What would that end up being? And so we're going to find out that as we multiply I times itself multiple times, we're going to see that there is a pattern that emerges. So we've already defined these two. I is equal to square root of -1 by definition of part of what an imaginary or complex number is in the first place. And I squared would just be undoing the square root that's on the -1, so that ends up being -1. But whenever we multiply it times 3, again, I cubed is like I squared times I. And we already know that I squared is a -1. So we're just multiplying that times I, and we get -I as a result. I to the 4th is the same as I cubed times I, or put another way, I squared times I squared. And you see that I squared times itself is like -1 times itself, which is 1. When we start with I5, we notice that I5, again, per our exponential rules, is just I to the 4th times I. And here, I to the 4th is just 1. 1 times I is I. And you notice that this is the same as this. And if we move on up and do I raised to the 6, that ends up being a -1, just like I raised to the 2. And I raised to the 7, of course, we break it down, ends up being -I, just like I cubed is -I. And one of the things that you start to see here is that every time we go up 4 in a particular power, we're going to end up with the same result. So for instance, we know that I squared is equal to I raised to the 6. And of course, we could rewrite that this way. Okay. And that's normally the thing that happens. And part of the reason for that is that in a complex number system, every time we multiply by I, from a geometrical standpoint, what we're actually doing is we're shifting or moving that complex number in that system by 90 degrees. Okay. That's a real number interpretation for what's actually going on. I don't want to get into the whole real and complex number plane right now, because we're just trying to work with how to computationally work in complex numbers. But just understand that whenever we multiply by I, you can sort of in your mind imagine you shifting a number or moving it in that plane by swinging it 90 degrees. All right, so let's move forward here. We see that in general, we know that for powers of I, we know that whatever the base is, and that's anything from I to the fourth, no matter how big the number is, we should be able to rewrite it in terms of 2 plus 4 times a multiple, or 3 plus 4 times a multiple, or 4 plus 4 times some multiple. And the easy way to do it is whatever number you have in the exponent, just divide it by 4. Whatever the remainder is, that's what you'll use to be able to evaluate. So to give you a simple example of that, we look at I raised to the 27. So of course, if we take 27 divided by 4, that's going to be 6 with a remainder of 3. So we know that I raised to the 27 is just the same as I raised to the 3, okay? Because ideally what we're doing here is we're saying I raised to the 27 is equal to I raised to the 3 plus 4 times 6. That's literally what we're saying. And so this part here, we know that that's just going to be a repeat. So we just kind of forget about that. And we're saying, all right, well, this has to be whatever I raised to the 3 is. So that's essentially what's going on. And of course, from a chart that we had above, we know that I cubed is just equal to a minus I. All right, so now let's get some practice with these. So we have I raised to the 25. So if we take 25 divided by 4, we know that 4 will go into that 6 times with a 1 remainder. So we know that I raised to the 25 is just the same as saying I raised to the 1, which is just I. Because anything raised to the 1 is just itself. Okay. And I'm going to go ahead and erase this because that didn't turn out too well. Yeah, with the remainder of 1. Same thing with B. If we take 19 divided by 4, we know that that goes into that 4 times with a remainder of 3. So I raised to the 19 is just going to be the equivalent of I raised to the 3. And we know that I raised to the 3 just ends up being negative I. Because if you remember, I is square root of negative 1. I squared is negative 1. I cubed is just I squared times I, which is negative 1 times I, which is negative I. And I raised to the 4 is just going to be I squared times I squared, which is negative 1 times negative 1, which is 1. So this is the basic chart that we're going by here. Now for this next example, notice that this is I raised to the negative 27, okay? So here, anytime we have something raised to a negative exponent, of course we know we could rewrite that as 1 over, same thing raised to the positive exponent. And if you remember, this was a similar example that we had. We know that take 27 divided by 4, 6 with remainder 3. So this is the same as I cubed. And of course, here 1 divided by I cubed will just give us a negative I. Okay. Now, with this still kind of poses a problem, and I'm saying that only because we actually are doing division here, and we technically have not talked about that. Okay. So the way that I'm going to go about doing this problem, to try to avoid division, is to remember that 1 is the same thing as I raised to the 4. Okay. So I'm going to replace this 1 here with I raised to the 4. And then using our exponential rules, I know that I could rewrite this as I raised to the 4 minus 1, which is the same thing as negative I raised to the 3. And we know that I raised to the 3 is just a negative I. And our final result here, since a negative times a negative is a positive, ends up being a positive I. Okay. Now, when we discuss division later on in this particular video, then you'll see another way for us to be able to get to the same answer. All right, so now if we want to do I raised to the 95, kind of the same thing. Take 4 divided by 95. And so 4 goes into 9 2 times with a 1 remainder. Bring down the 5. 4 will go into 15 3 times with a 3 remainder. So here I raised to the 95 is just going to be equal to I raised to the 3, because we got 23 multiples of 4 within that. And this final answer is just a negative I. For our last one here, and this again is just to show you that it doesn't matter how big these exponents get, it's all pretty much the same. We need to take 15,783 and divide it by 4. So 4 goes into 15 3 times with a 3 remainder. Bring down the 7. 4 goes into 37 9 times with a 1 remainder. Bring down the 8. 8 will go into, 4 will go into 18, let's say 4 times, and I'll just bring that up here with a 2 remainder, and then this 3 here will have to pass down, and then 4 will go into 23 5 times with a 3 remainder. So we see that this number here again is just same as I raised to the 3, which is just minus I. So no matter how big the numbers are in the exponent, as long as they are integer type numbers, we can deal with. All right, so now we want to discuss complex numbers as far as being able to divide them. And I'm just going to read this verbatim here to kind of make my point. So we want to recall that the complex numbers is an extension of the real number set. And with this expansion of bandwidth within the real numbers to become complex numbers are things gained and lost. Okay. What we gain with the complex number system are extra numbers in the system that we could describe how to come up with solutions to an equation like this. Okay. And just to make my point, if we were doing solving quadratic equations here, we would know we would take the principal root of both sides of that, and we would end up with plus or minus square root of -2. And of course, this is not a real number, so we would have to learn how to express that properly. Okay. Now, we gain the ability to be able to describe solutions to equations like this that would normally not have an actual valid solution. But what we're actually losing here is the property of order. Meaning, we know that -1 is a smaller number than 2. Or 200 is a number that is greater than or equal to 199.999. Okay. And so with complex numbers, because of the rules of an algebra, one of those rules is the rule of order, being able to know which element is larger or smaller than the other, or which elements are equal. And we lose that whenever we go up a dimension to the complex numbers. And so the issue with that is that since we don't know what's bigger or smaller, we really don't have a good way to quantify, in terms of what we know in real numbers, how much a complex number is. Because of that issue, it kind of doesn't make a whole lot of sense, from a real number perspective, to take a complex number and divide it. Because how are you going to divide something by something else and you don't know how much that actually is? So for instance, if I wanted to take a candy bar and I wanted to divide it into, let's say, 4 pieces, you know how much that is. But if I said, hey, let me take a candy bar and divide it into 1 plus 2i pieces, well, you don't really know how much 1 plus 2i actually is. So there's no way technically, using a real number perspective, that you can actually do that. Okay. And so that's basically what I'm trying to say here in all this verbiage here. Now, it turns out that we do have a workaround. And so if you recall here, recall that the product of any complex number, and I'm just calling it z here, and its conjugate, which we call z bar, yields a real number. Okay. Well, using this fact will help us to indeed be able to divide complex numbers by multiplying the conjugate of the denominator of both the numerator and denominator of a complex number in quotient form. And so I'm going to show you what that actually looks like here. So for this example, we see that we have a complex number in the denominator. The conjugate of that complex number is going to be 2 minus I. So what we're going to do here is we're going to equivalently multiply this complex number by 1, because we know 1 times anything is just that anything. But the way in which we're going to write 1 is we're going to write 1 as conjugate of denominator divided by conjugate of denominator. Okay. And in doing this, we know that the numerator, we're just going to work with it as we normally would if we were multiplying. The denominator, the denominators here, we know that they're complex conjugates. So again, we could use this shortcut that a plus bi times a minus bi is just a squared plus b squared. Okay. So here this would just be 2 squared plus 1 squared. And in the denominator, 2 squared is 4, 1 squared is 1. So 4 plus 1 is 5. And then in the numerator, we'll go ahead and distribute. So that would be a 6i minus 3i squared. And remember, I squared is -1. And of course, a negative times a negative ends up being a positive. So you end up getting 3 plus 6i, all that divided by 5. And then finally, to keep this in true complex number form, we want to separate the real part and the imaginary part. So here we would say 3 divided by 5 plus 6 divided by 5i. And that is the proper way to write that answer. Depending upon if you're trying to put these answers into, let's say, a learning management system like a MyMathLab or ALEKS or anything like that, they may or may not accept this form of the answer, but most all of them should accept this true form of complex number here. So it's good habit to actually get into, to actually write your complex numbers out like this. All right, so for example B, notice that we have an imaginary number, negative I, which is the same as 0 minus I, complex number wise. And here we know that the conjugate of 0 minus I is just 0 plus I, or just simply I. So here we're going to multiply the numerator and denominator by I here. And of course, the denominator is just going to be a negative I squared. And numerator here is going to be a minus 2I minus 4I squared. And I squared is a negative 1 in the denominator here. And we'll do the same thing here. Of course, negative times a negative ends up being a positive. So we have 4 minus 2I here. And negative times negative ends up being a positive. So this just ends up being 1 minus 2I at the end of the day, because anything divided by 1 is just itself. So for our next example, if we wanted to figure out what this actually is, we multiply numerator and denominator by the conjugate, which is 5 minus 3I. And we know in the denominator that's just going to be 5 squared plus, this should be a plus, not a minus here. It should be 5 squared plus a negative 3 squared. In the numerator, we'll just do the FOIL method. So first, outer, inner, so on and so forth. Let's erase that. So if we do that, in the numerator, we'll end up getting 5 plus 3I plus 20I plus 12I squared. And here we know that the two middle terms in the numerator combine to be 23I. I squared is a negative 1. And in the denominator, 5 squared is 25. Negative 3 squared is a positive 9. So here we see that 12 times negative 1 is just minus 12. So 5 minus 12 is a negative 7 plus 23I. And all that's divided by 34. And splitting the number up into true complex number form will end up giving us a negative 7 over 34 plus 23 over 34I as our resulting complex number. So with our next example, kind of the same thing. We have a negative 1 plus 3I. And for our denominator, we know that it's just going to be 1 squared plus, negative 1 squared plus negative 3 squared. And in the numerator, we will multiply using the FOIL method as you normally would for a binomial. So negative 2 times negative 1 is a positive 2. Negative 2 times a positive 3I is a minus 6I. And let's get that working here. And then minus 5I times a negative 1 will be a positive 5I. And then negative 5I times positive 3I is a minus 15I squared. And of course, from there, we just simplify and combine like terms. So we have 2 negative 6I plus 5I is minus 1I, or just minus I. And then, of course, I squared is negative 1 there. In the denominator, we have 1 plus 9, because negative 1 squared is 1, negative 3 squared is 9. Back to the numerator, we see that this negative times this negative ends up being a positive. So all this just ends up being 15. And of course, 15 plus 2 is 17. So we end up with 17 minus I divided by 10. And of course, written in true complex number form, we will have it as 17 over 10 plus 1 over 10I. So for our next example, same thing. For here, since the denominator is 1 plus 10I, the conjugate of it is going to be 1 minus 10I. And in the denominator would just be 1 squared plus 10 squared. And here in the numerator, see that you just have a real number being multiplied times a complex number. So we can just distribute 4 to both terms there. So that would be 4 minus 40I. In the denominator, we have 1 plus 100. 10 squared is 100 and 1 squared is 1. Still have the 4 minus 40I. So we see that denominator ends up being 101. And we know that'll be 4 divided by 101 minus 40 divided by 101I as our final answer. Okay, so for our last example for dividing complex numbers, we see in the denominator we have a 4I, so that means we're going to multiply both numerator and denominator by a negative 4I. Because remember, 4I is the same as 0 plus 4I. So minus 4I would be this. And of course, conjugate just means that everything is the same except for those signs. So for here, since we just have the imaginary part, it's easier for us just to go ahead and just multiply these together. So 4 times a negative 4 is negative 16. And then, of course, I times I is I squared. In the numerator, we have an imaginary number being multiplied times a complex. So we're going to distribute that imaginary number to both terms. And that ends up giving us a negative 28I. Let's try that again. So negative 28I. And then that'll be plus 8I squared. And in the denominator here, I squared is a negative 1. I squared is a negative 1. And I've got to put the I here. So let me go ahead and clean that up. So we end up having negative 8 minus 28I all over a positive 16. And that ends up giving you negative 8 over 16 minus 28 over 16I. And then from here we want to reduce. So we know 8 divided by 16 is the same as 1/2. And we also know that 28 and 16 have a common factor of 4. So 28 goes, we'll say 4 goes into 28 7 times, and 4 goes into 16 4 times. So this would be your final answer for dividing those two complex numbers together. So now that we know how to add, subtract, multiply, and divide complex numbers, the last thing that we need to know how to do is how do we deal with numbers to where we have square root of a negative number, and we're either going to, let's say, take two of those types of numbers and either multiply them together when they're not in their actual complex or imaginary form. And so we're going to see how do we properly deal with that. So I'm just going to read the verbiage here. It says, note that the principal root of 4 is 2 because square root of 4 is 2. Thus, the principal root of 16 is 4 because square root of 16, if we rewrite that, it's going to be square root of, under the radical, 4 times 4. And of course, we can use our radical rules and separate that into square root of 4 times square root of 4, which is 2 times 2, which is 4. Now, I'm going through all of that basically to say that I'm able to do what I did there in the first two sentences because I know that both square root of 4 and square root of 16 are real numbers. And particularly, I know that 4 and 16 are non-negative, meaning that they are a number that is greater than or equal to 0. Okay. Now, whenever we start to take the even nth root, or in this case, the square root of a negative number, we know from what we just got through talking about that those types of numbers are not real numbers. So they can't follow the same type of process for trying to evaluate a radical expression as we would for trying to evaluate radical expressions that are actually real numbers. Okay. And that's really the point of this particular section of this video here. Okay. And so that's why I'm saying that since the root of a negative number is not a real number here. Okay. Oops. And that's going crazy. So let's try to clean that up. Yep. So since the root of a negative number is not a real number, we can't use this particular property directly to simplify a number like this. Okay. So when we do this, we're going to have to extract out the negative portion of that number, but we have to do it the correct way. And so this is our correct way of being able to do that. So essentially what we're saying here is that square root of negative b is the same as square root of negative 1 times b, like this. We know we can do that since b in itself is a real number. But now what we have to do is separate it this way, okay? And of course, it's this part here, the square root of negative 1, that's the thing that's different than what we've seen before whenever we're just dealing with radical expressions that are just real numbers. And we have the even nth root. So in general, what we need to do is just be able to take our expression, in this case square roots of a negative number, and rewrite them with that square root of negative 1 part being translated as I here. So for this first example, I'm going to rewrite this as square root of negative 1 times 64, which is the same as square root of negative 1 times square root of 64. And of course, square root of negative 1 is just defined as I. Square root of 64, that's just defined as 8. So we could just rewrite that as 8 times I. And of course, that makes sense because if we took 8I times itself, we would get 64 I squared. And if you remember, we know that I squared is just equal to negative 1. And so we see that 8I is the imaginary number that we would have to multiply times itself twice to get negative 64. Okay. So for our second example, we'll rewrite this as square root of 8 times square root of -1. And of course, this time I'm just flipping it so that I can have the I on the right side instead of the left. We know that square root of -1 is just I. And 8, although it is an irrational number, we can break it down some more. So we know that square root of 8 can be broken down to square root of 4 times square root of 2. And then, of course, we write the I at the end. Square root of 4 is just 2. So this ends up being 2 times square root of 2. And all that times I. And that would be what square root of -8 would look like in terms of I in the simplest terms. Similarly, for example C, we have this is square root of 32 times square root of -1. And of course, square root of -1 is just I. 32 is 16 times 2. So we could rewrite square root of 32 as square root of 16 times square root of 2. And then put the I on the end. And of course, square root of 16 is just 4. So our final answer here would just be 4 times square root of 2 times I. And then for our final example here, hold on. Move this down just a bit. Here we would have square root of 19 times square root of -1. And of course, square root of -1 is just I. And since 19 is a prime number, there's nothing else that we can do to break down square root of 19 anymore. So our final answer just ends up being square root of 19 times I. So now what we want to do is take these imaginary numbers and multiply them together. But you notice that these imaginary numbers are not in their, complex or imaginary number form. They're in the square root of a negative number form. And so one of the things that we need to understand is when we see this sort of thing, the first thing we have to recognize is that, hey, we are multiplying two numbers that are not real numbers, okay? If you don't recognize that, you will try to do what I am about to write here, okay? Now notice that what I'm about to write is not correct, okay? So when most people try to do this, if they don't think about the fact that this is not a real number and that's not a real number, what they will try to do is something like this, okay? They'll try to say this as if these two are real numbers. And of course, -4 times -14, that ends up being, what is it, a positive 64 here. So, excuse me, that's actually a positive 56, not 64. Let's get that in. They'll try to do this, and then from here, try to deal with this the best way that they can. But my point here is that this is incorrect because of the fact that whenever we look at all of this, we're trying to deal with this as if these are actually real numbers and they aren't, okay? I'm going to go ahead and finish this. This could be rewritten as square root of 8 times square root of 7. And this part is just 2 square root of 2. And square root of 2 times square root of 7 is square root of 14. So we end up with this as a result, okay? Now, of course, the problem is that if I was to take both of these two things and multiply them together, notice that what I'm saying here is that I have two numbers that aren't real. They're going to end up equaling something that is real. But if I actually look at this in terms of the definition that we talked about, we would end up getting two different things. So notice that this is not correct. Now I'm going to do this the correct way so that you can see the difference in the answers. Okay. So here, if we were to work on this properly, we would first have to say this is square root of 4 times square root of -1 times square root of 14 times square root of -1. And we know that the square root of -1s is just I. Square root of 4 is just 2. And so what we end up with is 2 times square root of 14 here. And we have I times I, which is I squared. And of course, we know that I squared is just -1. So that ends up being a -2 times square root of 14. And notice that this is the correct way to do it. And notice how we got a different answer than what we did here. Okay. And again, the difference is that here we are treating square root of -4 and square root of 14 as the complex or imaginary numbers that they are, whereas here we are not. So again, that's why this way is not correct and this way is. So moving on to our second example, again, we'll have square root of 8 times square root of -1 times square root of 2 times square root of -1. And of course, the square root of -1s just go to I. And we saw earlier in a previous example that square root of 8 can just be rewritten as 2 times square root of 2. So we just have 2 times square root of 2 times I squared. And we know I squared is just equal to -1. So that final answer just ends up being a -2 times square root of 2. Looking at our next set of examples here, we do the same thing. Have square root of 7 times square root of -1 times square root of 5 times square root of -1. Of course, square root of -1s ends up being i's. Square root of 7 and square root of 5. 7 and 5 are both prime, so there's no way we can break these numbers down. So the most we can do is just multiply them together. So square root of 7 times square root of 5 is square root of 35 times I squared. And again, we know I squared is just -1. So -1 times square root of 35 is a negative square root of 35. And then finally, for example D, we know that we can break this up into square root of 24 times square root of -1 times square root of 16 times square root of -1. Both of these being I, square root of 16 is 4. And we know that square root of 24 is the same as square root of 4 times square root of 6. Okay. And square root of 4 just ends up being 2. So here, this just ends up being 2. So that's 2 times 4, which is 8, times the square root of 6, which is here. And then, of course, I squared is equal to -1. So that ends up being a -8 times square root of 6. All right, so now that we have all the basic skills that we need to be able to evaluate expressions that have negative square root signs in them, we're going to go ahead and express these numbers that are not in imaginary or complex number form and force them to be in imaginary or complex number form. Okay, So we'll start off with this first example here, and just to be clear, this is square root of -5, all that raised to the 3. And of course, we know that we can rewrite this as square root of 5 times square root of -1, all that raised to the 3. And using our exponential rules, we know that this is square root of 5 raised to the 3 times, of course, square root of -1 is just I, so that'll be I cubed. So from here, we know that square root of 5 raised to the 3 is like square root of 5 times square root of 5 times square root of 5. And I cubed, from what we talked about earlier, is just going to be a minus I at the end of the day. Because we know I cubed is just I squared times I, and I squared is a -1. And -1 times I is a -I. Square root of 5 times square root of 5 is square root of 25, which you know that's just simply 5 at the end of the day. So we have a -I here, so we just put the I there and a negative there, and then we'll have 5 times square root of 5. And so this is how this number would look. If you wanted to be very formal about it, you would write it like this, but since 0 minus anything is whatever that minus anything is, so that's why here this answer is acceptable. Now, example B, this is what problems whenever we are trying to solve quadratic equations using the quadratic formula. This is what this is an example of what those types of expressions would look like. So we'll come here, we'll say 9 minus, and then this would be square root of 18 times square root of -1, all that divided by -6. Of course, square root of -1 is just I. And then from here, we know that square root of 18 is the same as square root of 9 times square root of 2. The square root of 9 is just 3. So we have 9 minus 3 times square root of 2, I, divided by a -6. And then from here, we will just simplify as much as we can. So here we have 9 divided by -6 minus 3 times square root of 2 over -6, I. And of course, 9 and 6 both have a common factor of 3. So 3 goes into 9 3 times. 3 goes into 6 2 times. See, the negative times a negative here will give us a positive. And 3 divided by 6 is just 1/2. And of course, we got the square root of 2 there with the I. So our final answer ends up being a -3/2 plus square root of 2/2I. So for our next set of examples, we'll start with example C. We're going to evaluate everything that is under the radical first, and then we'll deal with what that result is when we get there. So square root of -1 is just 1, minus 4 times 1 is 4. 4 times 2 is 8. Okay. So we see here that this just ends up being 1 minus square root of -7. And we know that square root of -7 can be rewritten as square root of 7 times square root of -1. Which this part is I. So this just ends up being 1 minus square root of 7i. Finally, for example D, you see we could rewrite square root of -16. It's just square root of 16 times square root of -1. Square root of 16 is 4. Square root of -1 is I. So we end up having 4 plus or minus 4i divided by -4. And then we'll split that up into separate fractions. So this ends up being -1. And of course, this negative times the plus or minus here just switches the pattern of that. And that's just going to be 1i. And we could simply just rewrite this as 1 minus or plus I at the end of the day. And if you're wondering, that is the same as 1 plus or minus I. But we're just flipping it to know that if we had an order in doing this, the one with the subtraction sign will come first. All right, so if you have been watching this video for the past hour and 10 minutes or so, thank you for hanging in there. I know it's a lot of information to cover, but hopefully this has been beneficial to you. Wanted to cover the last topic here, which talks about the discriminant and complex solutions to equations. So like I've mentioned earlier in this video, a lot of this whole thing about the complex numbers even coming into being is because of the whole notion of, hey, with the quadratic formula, we have all these numbers that end up having negative numbers under the square root sign in that formula. And so we know in particular that whenever that expression we call discriminant is negative, meaning that it's less than 0, we're expecting complex conjugate solutions, okay? And just so that you have an example of what I'm talking about here, I'll go back to one of the problems that we did here, example D. This is an example of complex conjugate solutions because 1 plus I and 1 minus I are conjugates of each other, okay? So that's where that actually comes from. So what we want to do is, now that we know that, all right, we know that we're going to have complex conjugate solutions here, then we want to, 1, find the complex conjugate solutions of this equations, if any, if we're in a situation like this, and 2, we want to determine if a given complex number is a solution to a particular equation, quadratic equation it is. So now that we kind of know what the solutions to a quadratic equation would look like, again, we want to be able to either go through the process of finding complex conjugate solutions, basically solving this equation, and not really caring if the discriminant under the radical is negative or not, because now we know how to deal with it, okay? Or we want to be able to evaluate an expression to see if the given complex number is a solution to the equation. So what I mean by that is we want to take a complex number, plug it into a function, or evaluate the function with that number and see, does it end up coming out to the outcome that we want, which is 0 here, okay? So I've already written these in, so I'll just kind of talk through them. So the first one, we want to know for this particular quadratic function here, and this one, we want to evaluate them at these following complex numbers to see if indeed they will be solutions to the quadratic equation, whatever you're seeing for p of x, t of x, or w of x equals 0. So for part A, we see that we're looking at the function w of x, and they're saying everywhere where we want x to be, replace it with 2 minus I. So we've done that here. Since this is x squared, we know x is 2 minus I, so we just put 2 minus I, quantity squared. Then we have minus 6 times x, so again, minus 6 times 2 minus I, okay? And I don't know why that's squared. It shouldn't be. So I'm just going to scratch that out. And then, of course, we have plus 14. So if we're looking here, what we are seeing is this 2 minus I squared. If we factor this out, that will be these first 3 terms here. So that's basically 2 squared plus 2 times a negative 1I times 2, and then negative I squared. So that's what you end up seeing here. So it's like a negative I times a negative I, and that ends up being positive I, and then you square it. So that's how that ends up there. The next 2 terms are these two. You have the negative 12 plus 6I. That's what these are right here. And of course, then you have 14. Now, after we simplify everything, you see that we get 4 minus 4I minus 1 plus 2 plus 6I. And when we combine like terms, we get 5 plus 2I. So we're doing all that work to basically say, all right, well, here, did this equal 0? And of course it didn't. So what that tells us is that when x is equal to 2 minus I, that's not going to be a solution to this quadratic equation. Okay. If we end up getting 0 for an answer, whenever we plug in a complex number into a quadratic expression, then we know that that particular complex number is a complex solution to that equation. And of course, example B is a good example of that. So for here, we're using the function p of x, and this says everywhere where you see x, replace it with negative 2 plus I. So we have negative 2 plus I squared plus 4 times negative 2 plus I, and then plus 5. Again, just like how we did up here in this example, we'll multiply negative 2 plus I quantity squared. We'll multiply that in the same way as we did 2 minus I squared. So here we end up getting negative 2 squared plus 2 times I times a negative 2. And then for this last one here, there should be an extra parenthesis here. But that should be 8 times negative 2, which is negative 8. And then same thing here with the 4 times I. Okay. So that's where those 2 terms come in there. And of course, if you simplify everything, you'll see that at the end of the day, you end up getting 0. Okay. So that lets you know, as I'm stating down here, that negative 2 plus I is an actual complex solution to this equation here. Okay. And then for the last example, we just plug in 3 minus I into our t of x function to see what that outcome is, and we see that the outcome is 17 minus 12i. And of course, since it's not equal to 0, then we know that 3 minus I would not be a solution to the equation t of x is equal to 0. Okay. And so the last thing that I want to do here is kind of verify why we know negative 2 plus I is an actual 0 by actually doing the quadratic formula. So you can see how what we were working on previously ties into what I'm trying to tell you now. So we're looking at the function p of x, which is x squared plus 4x plus 5, and we want to see what the zeros are for this. So here we know from a quadratic formula that that's going to be minus b plus or minus b squared minus 4ac, all of that over 2a, and we need to identify what our a, b, and c are. So in this case, we're following the profile of ax plus b squared, or ax squared plus bx plus c. So that means a has to be 1, b has to be 4, and c has to be 5. And we literally just plug and play at this point. So we got the negative b plus or minus b. That didn't turn out too well. So we got b squared minus 4a, which is 1, c, which is 5. And all that divided by 2 times a, which is 1. So we got negative 4 plus or minus square root of 16 minus 20. All that over 2. Of course, we know 16 minus 20 is a negative 4. And we know square root of negative 4 is the same as square root of positive 4 times square root of negative 1. This is 2. All that divided by 2. And our final answer, if we split this up into 2 separate fractions, is a negative 4 divided by 2 plus or minus. And of course, the square root of negative 1 is just I. So this would be 2 over 2I. That will give us a negative 2 plus or minus 1I, which is just negative 2 plus or minus I. And if we go back to the problem that we were talking about before, we'll see that one of those answers, which the 2, negative 2 plus I, was the one that we were asked to evaluate, and we saw that we got 0 for that outcome. And so that's how all this stuff is connected, as far as being able to take an expression that has negative square roots and rewrite it into a complex number form, so that we could, have it in a form that's understood and widely accepted. Okay, and so with that, this concludes this video on being able to work within the complex numbers. I know this was a long video, but hopefully this has helped you out a lot to be able to understand some of the basics about how to work with complex numbers and give you an idea on some of the ways that we use it. All right, take care.